Okay, let's thank Josh again. And the last talk of the session will be by Thibaut Pérami about a context cleaner.
Is that still okay?
Yeah, can people hear me? Yeah. So hello and welcome to my talk about general white box automation and the first step I've taken in that direction, which is a typeclass-guided context cleaner. So for the context, I'm a PhD student at Cambridge, and I'm working on low-level semantics like assembly and weak memory style of stuff. And so I have a lot of goals that are relatively trivial, but still annoying to deal with by hand. So I've explored automation to solve those kind of problems. So what do I mean by general white box automation? I mean basically a hint-based proof search. So something that is general, can prove anything, provided the correct hint, and is white box. So it's as transparent as possible, and users using it are expected to understand exactly how the proof search works and debug it themselves. In particular, such a system would have the usual caveats that adding a hint can break later proof, and that adding rewrite hints can make rewriting not concurrent. And that's not a problem as long as the user is able to debug those problems. So I'm not looking for any meta theory that would prevent those things from happening. So hint-based proof search places itself around here on the automation trade-off. So here I draw more on the left things that are more black box, more automatic, but have a high-level specification. The most extreme case being a SAT solver that is decidable and have a very simple high-level IP, a Boolean expression. But internally, it's quite complicated. But the user of the SAT solver needs only to understand what a SAT problem is. It doesn't need to understand how a SAT solver works, which is quite important. On the other hand, the more you go on the right, the more theory coverage you will have, but the more failure you will have. And so the user needs to increasingly understand how the tool works to debug it. And so the tools need to be increasingly white box and debuggable. I mean, the extreme being doing the proof by hand. And I think hint-based proof search has a very important point on that line that is not explored enough. So I try to do that. So what do we want from a hint proof search system? We want a good hint system, and here are some of the properties I'm interested in. So it needs to support backwards and forward reasoning as well as rewriting. I mean, ideally having something like int extern where you can inject an arbitrary tactic in your search is useful, but not necessary. And you also want to control well when hints are applied or not. So you want at minimum local export on global locality and some other things like, for example, you want to be able to enable a hint on a single tactic call. And ideally, you want to be able to group hints together, like group 5 hints together, enable them and disable them at the same time, including on a single tactic call. There is one last important thing with hints, which is that hints can be safe or unsafe. And the idea is that the user specifies whether a hint is safe or unsafe, and the system trusts the user on that. And that is critical for performance, because on a typical proof search, I expect to run something like hundreds of safe hints and very little unsafe hints, maybe even 0. And so on safe hints, I don't want to do any backtracking. If a safe hints apply, I apply it, and then I forget I applied it. Whereas unsafe hints, I do want to do backtracking. And the user is promising that somewhat applying a safe hint maintains probability. So the new set of generated goals are equivalent to the original one. So some example of safe action you can take is splitting a goal or doing a substitution, whereas taking the left of a disjunction or introducing a viva are fundamentally unsafe. So I try to think about how to build a system that can do all of this using the existing Coq tactics. So I tried and kind of failed. So first, I look at Auto. So Auto is a quite nice white box proof search tool. It's easy to debug. You understand what it does. It applies hints in order, but it has some problems. In particular, Auto does not support any concept of safe hints. So you can kiss goodbye to any idea of applying hundreds of hints in a single proof search. Also, Auto naively only supports backward reasoning. Yes, you can hack it with hint extend, but if you just add a random x extend every time you want a forward rule, performance will blow up quite quickly. But it is good to keep in mind that Auto is a very good point in terms of debuggability and priority systems, because both of those things are very good for Auto. So I tried to explore other things. In particular, I tried sauto from the CoqHammer project. Sauto is quite nice. It's very efficient on the theory it supports, but it's a bit hard to extend. Like, it's really black box. It's hard to debug when it fails. And it has what I would call a subpar hint system, in the sense that there are a lot of styles of hints you can't add at all. For example, if you want to do something like int extern, it can only be safe. You can't have unsafe int externs, and there is a bunch of other limitations. And it really feels in the API that sauto was designed as a solver, which is fair enough because it was designed to reconstruct SMT proofs from CoqHammer, not that much to be used as a standalone tool. So I would say that auto is a bit too much on the right of this line, and sauto is a bit too much on the left. And so I'm trying to find some middle ground that has both good debuggability, good in system, but it's still powerful enough to do the proof I'm interested in. So I also looked at what other proof assistants do. In particular, I spent 4 months working on Isabelle, and I have some intensive experience with fastforce and related tactics. So I'm saying fastforce but there is actually 10 different names that more or less call the same proof engine with different priorities and heuristics. Fastforce is maybe the most well-known, but not the only one. Then Lin also developed aesop, which is a decent whitebox search, but I've never used it, so I can't talk much about how it's actually usable. And then auto and sauto I already talked about. And so if we start comparing them, so first we note that both fastforce and aesop supports all the style of hints I want without any limitation, which is naively not the case of auto and not really the case of sauto. Like there are some asterisks here. Furthermore, an interesting data point is that fastforce does not support arbitrary tactic, as far as I know. aesop does, auto does, and sauto has this safe limitation. And despite that, fastforce is still considered a good tool. So that's an interesting point. Then the safe and unsafe distinction is supported by both fastforce and aesop, and I think that's the critical bit that makes this tool actually good in practice, and what's missing in auto. In terms of priority system, fastforce doesn't have any explicit concept of priority. They have kind of accumulated 25 years of heuristic that guess in which order to apply hints, which make it decent in practice, but it's not what I would call white box. And in terms of debuggability, fastforce is already quite annoying. Like if you call fastforce and it fails, it's quite hard to understand. Whereas if you call auto and it fails, it's really easy to trace it and understand exactly the sequence of steps it tries. So there is some things to be done there. aesop, I have no idea, I've never tried. So that's kind of the landscape I felt I was in. And a last very important point is that both Isabelle and Lin have a good built-in simplifier that those proof search tools are actually actively using, where Coq doesn't really have what I would call a good built-in simplifier. Like, yes, you can hack rewrite strat to do some stuff, but it's not really great. So that leads me to what I think we need to do to get a good general white box proof search architecture in ROC. This is not new. I'm just basically stealing the architecture of the other proof tools. So first, we need a good simplifier, so something that can do efficiently rewriting and computation, so more or less what you would expect from rewrite strats and CBN, all at the same time and efficiently. Once we have that, we need a clarifier, so something that can run all the safe proof steps in sequence. That includes calling the simplifier, but also things like doing safe reasoning, like what intuition does, doing safe equality reasoning, like what simplify egg would do, and some other safe stuff. Something that would look like Isabelle clarify. And once we have that, we can do a proof search by just running the clarifier, trying one unsafe step, running the clarifier, trying one other unsafe step. And here we need to think about depth first search or best first search and priority system to know in which order to try unsafe steps. In this talk and in my own work, I've focused only on the clarifier, so I won't talk much about the other two. So cdestruct is my clarifier for ROC. So it's designed by having a core tactic in LTAC2 that's not very long, like 50 lines of LTAC2-ish, and that applies some steps in order without doing any backtracking, and it pulls from a tape class in system which steps it should apply. So some example of what it can do is case splitting, so taking inductives in the context and breaking them down. Similarly for the goal, taking an n in the goal, splitting it up. Then it can do injection and discriminate. It can do computation, so it will happily call CBLN regularly. It can replace proposition, so take a proposition, replace it by another. This looks like rewriting, but it's not really rewriting. Like cdestruct has no built-in system to like rewrite under anything. It will just take a whole level proposition and replace it by another according to a tape class. So I've done some very hacky tape class hackish programming to remake that into somewhat a rewriting system, but it's not great, and we really in desperate need of a decent simplifier. Then it can do substitution, and it can do match case splitting, which are also quite usual things to do. So how one would you use it? So if you don't give any hints to cdestruct, it's basically useless. So there is a default database of hints that handle like standard logical connective, and then the user can add new ones. So for example, to tell cdestruct to break an end in the hypothesis as soon as it sees it, you just add this instance, and then cdestruct will pick it up. Then you can add a rewriting instance, so you tell cdestruct to replace is sum of O by there exists an O, so there exists an X such that O is some X, and then this instance will contain the actual equality proof. So when you do the dots, then Coq will ask you to prove the payload of that type class. The cdes case has an empty payload. And if you want to gate a tactic by an option to, for example, have multiple instances that you enable together, you can create an empty class and use that as a gate. And so, for example, the splitting of AND in cdestruct is gated by the cdes split goal option. And so this instance will only be resolved if the cdes split goal option is enabled. And so cdestruct will only perform that operation if you enable that option. And you can enable that option either by making up a dummy instance of cdes split goal globally, or by setting it when you call cdestruct. So you can call cdestruct with a set of hypotheses and some intro patterns for goal hypothesis to work on. And then you can do hashtag an option and hashtag other options to enable specific ints that you want for this specific type class call. So now I'll show, and so all of this about type classes is quite important because I found that it's a relatively decent in system in practice. Especially with discrimination tree, you can reach a relatively fast lookup in terms of which hints to apply. So it's not perfect, but it's also not terrible. So what it can do in practice, I will give some example about a dependent map implementation I've done. So a dependent map is a map where the type of values is dependent on the type of keys. So I just implemented using stdpp gmap. So if f depends on k, then I just have a carrier, which is a gmap of k to the dependent pair of k and f of x, and then you have a soundness predicate that says that the first component of the dependent pair is the key. And then I want to prove lemmas, like if I insert value v at a position k in the map and then look up k, I get v again. And so how to prove this? I just unfold the two definition. I get these big ugly things where I do a match and an inspect, and then I do some transport, and then the corresponding operation insert and look up on the underlying map carrier. And then I can just call cdestruct on this, and it will entirely solve it without doing any unsafe steps, because there is no unsafe steps to be done here. So what cdestruct will do, it will break up the match. And here I will first handle the sum case. So in the sum case, the match discriminant is insert with lookup is equal to some s, s being a dependent pair. Then it breaks up the dependent pair. There is nothing to do on x of type k, so it inserts it. Same for f. Then for E, I've taught cdestruct with enough hints about map theory, so it's able to simplify that, but it can't directly in place because E is actually used in the obligation that's in the transport equality. So what cdestruct will do is make a copy and simplify the copy and block the original. So, and in the copy, it knows enough about map theory to know that doing the lookup after the insert gives the same thing, and so it gives the equality of XST. So then the block things needs to be introduced because you can't work on it any further. And then you have XST equality. So the cdestruct is able to extract the equality of the first component and the substitution. So we substitute k to x and revert anything that's modified by that substitution. Then we keep processing. There is nothing to do here, nothing to do here. Then we again have an XST equality, but this time the first component unify. So this simplifies into an equality of the second components. I do use UIP. And then there is a substitution again to be done. So v into f. So we revert everything again. Then we reintroduce the block thing. Then we can do a computation. There is on the right .t2 of XST, so we can do the projection. Then we can peel out the sums. And then this transport, the source type is f of k, and the target the type is f of k. So the transport does simplify. And so we end up with v equal v. And then reflexivity. And the non-case is much less interesting because given map theory, cdestruct knows that this simplifies to false, and so can also solve the non-case trivially. So I found this tool to be useful in practice, not just on dependent maps, but on many other goals that I've encountered. And it kind of gives me a feel similar to Clarify from Isabelle, despite the lack of simplifier. So I kind of hacked together a bunch of logical programming and type class rewriting system to pretend I have a simplifier, but I don't. So that's something I want to keep working on. The lesson I learned is that for this kind of project, extensibility of your tactic is critical. So being able to add new rules without going back to the tactic definition is really important. And debuggability is also critical, otherwise I would have gone mad a long time ago. So you can run cdestruct step by step, so there is just a cdestruct step tactic, it will do one step. And you can just copy paste it 100 times and then run it by one and see when it does what you don't want it to do. And I've also learned a few things about opacity. So for this kind of stuff to work, you really need all constants to be opaque in type classes by default. That basically results in a 5 times speed up in both cdestruct and setoid rewrite, by the way. There are still some performance issues with discrimination tree, sadly. So in particular, if you start doing research on transparent terms, discrimination tree have a tendency of giving up the discrimination tree and just trying unifying with everything, which destroys performance. And lastly, I've discovered that injection completely ignores any concept of opacity, so I kind of re-implemented injection as part of cdestruct to have a version of injection that does respect opacity. So these are some of the things I had to do. Sadly, this is not my main topic, so I will have limited bandwidth to keep improving on it. But the thing that remains to be done is mostly actually do a good simplifier. So either by improving rewrite strats or keeping doing type class rewriting like I'm doing, but in a more principled way, or then there is the approach of reification and writing a verified rewriter. I don't really know which one is the best here. And for the proof search, I mean, one can think about improving auto and adding, for example, an option for safe hints, or we can write a custom tactic. And if we do that, then there is a question of LTAC2, LP, or CoqHammer plugin, which isn't fully clear to me. After watching the talk on LP, I'm not entirely sure that my choice of type class logical programming and LTAC2 was the best. But hey, it's done now. So far, this is not a standalone repository. It's part of my main project, but I'm happy to split it off if people want to try it and work with it. So are people interested? Let me know. Here's the code and the documentation.
Questions?
Thank you. Definitely interested in at least some of this. In particular, I was wondering if you could say a bit more about what you have in terms of forward reasoning, because to me, that's like the biggest thing that's missing from the standard ROC toolbox. I mean, you can wrangle auto to do a lot, but forward reasoning, I don't know a nice way to do that.
So yes, so I mean, you can tell cdestruct to break any inductive you want or not break any inductive you want. Then I mostly do so far my forward reasoning by rewriting proposition into a regular logical projective that then will be breaked up by cdestruct. Since I'm not doing any unsafe stuff yet, I won't take a risk of applying something that would like reduce the probability of the goal. That's something of a next step I'm thinking about, but I haven't done that yet. But I do a bunch of things that you would expect, like simplify AQ to do. Basically all of it, and a bit more because I also do a bunch of dependent simplification, like what you would expect. The kind of cleanup that dependent destruction does.
Okay, but there's no like, I don't know, apply the set of lemmas forwards until saturation and then go on and keep using those flags or something like that.
Saturation is something I've thought about, but I haven't really done yet because I'm a bit worried of blowing up, as all saturation thing is. I have some idea of doing it, but I need a bit more work, and I'm also afraid about how much it would kill performance. But basically, yes, cdestruct has really this idea of, I'm done with this hypothesis, I can move it to the context and not work on it anymore, so it really does it in order. And so this would be a good place to insert like saturation hypothesis, because then once the hypothesis is processed, you won't start looking again for saturation hypothesis. But I haven't actually tried that yet.
Something that I encounter a lot is like a particular goal is easy to solve using a particular assumption I have, but I don't want to add that lemma as a general hint, because then it will always try applying this, and that could easily go wrong in the completely wrong direction or something. I'm not sure if you have a nice way to represent it.
So right now, I don't think I have. So, I mean, one thing I do sometimes is rewrite a goal depending on hypothesis I picked up. So like if this hypothesis is in the context, then I can simplify that goal into this other simpler goal. That I can easily do. But I don't, I mean, since this is a clarifier and not an actual proof search, I don't have generic way of just applying a lemma based on some condition. But I do intend to, if I do a proof search, which is somewhat my intention, then I do intend to support these kind of things.
Okay, cool, thanks.
I think time for one last question.
I think you should actually take a look at Janus Lindberg's thesis and aesop, because it has basically exactly the same motivation and like design as what you've been talking about.
I've read the paper, but not the thesis.
But what I also wanted to mention that one of the downsides that we found with aesop is that you really need to have integration with the library. Like, you know, it's not good enough to just have a white box automation, because if you need to add hints for it to be useful, then if the library doesn't have the hints, then people aren't going to be bothered to add the hints on the spot when they're using it in application. So it's really important that like you coordinate with the libraries that you're like the upstream libraries that that users are going to be using with your tool.
No, I mean, to be fair, I mean, in my own project, I'm perfectly happy to adding the hints myself because I know it's worth it. Teaching people that it's worth it to write hints is a problem I haven't considered that much yet.
And a lot of users will not necessarily know what are the, you know, they won't actually know enough about how to write hints correctly and how to construct conflict rewrite systems. Blah, blah, blah.
It is, I mean, unless you are provided the hint database that already works out, it is a power user tool. I'm afraid of that. But it's not because it's only useful to people that are power user that it's not useful to make.
Okay, let's thank Thibaut again.